Welcome. In this video, we will take a look at section 3.4, which is looking at arc length and area of a sector. So let's consider the arc length first and how we define it. So the relationship between a central angle theta that we have drawn in our picture in radians, the radius r, and the arc length we call s has the following relationship. That's theta is equal to s divided by r. So that means that the radius, r, when divided by that arc length, we will have that angle theta in radians. This is really important that we have this angle in terms of radians. So this, we can point out kind of a special property here and consider, well, what if we were on our unit circle? If we were on our unit circle where our radius is equal to 1, if this radius equals 1, we would have that the theta angle is equal to the arc length divided by 1, or just the arc length in radians. So that's a special property that we can keep in mind. This was really similar to what we covered in class with 3.3, where we had this idea of our arc length, t, measuring the cosine of t equaling the x-coordinate and the sine of t equaling the y-coordinate in our unit circle. So this is the same concept that we took a look at here. So another way we can represent this arc length formula is that the arc length s is equal to the radius length times the theta angle in radians. So let's take a look at an example to work with this arc length concept. So we'll take a look at the first one here. This says find the arc length, or the length of the arc cut off by an angle of 315 degrees and a circle of radius 5 inches. Okay, so we really have the two needed components for arc length, the central angle and the radius of our circle. But we do have to do one step in converting this angle from degrees to radians. So let's do that here. We would have 315 degrees over 1. If we wanted to consider converting this to radians, our conversion ratio is pi radians to 180 degrees. And if we take a look at 315, this number can reduce, and so we will actually reduce this number. And this number, they both have factors of 45. If we divide by 45 here, divides into 180 4 times, and it'll divide into 315 7 times. So this angle 315 degrees is equivalent to 7 pi over 4 radians. And we can double check this. We're still getting familiar here with our unit circle. If we wanted to check 315 degrees, 7 pi fourths, those two things are equivalent, 7 pi fourths and 315. So as we get more familiar with this unit circle, and I encourage you guys to just continue to familiarize yourself with this unit circle, it's going to be really important to know these angles and the relationship with sines and cosine. That will really benefit you in the long run here. So we have 7 pi over 4 for our angle. And now we can actually use our arc length formula. So we know that arc length s is equal to the radius, that's 5 inches, times 7 pi over 4 radians. And we multiply that through, 5 times 7 is going to give us 35 pi over 4. And the units here of arc length are just going to be the units of our radius. So this would be inches. So we can leave that as complete. That's our arc length cut off by this angle of 315 degrees at a radius of 5 inches. Let's take a look at a second example with arc length. We want to find the length of the radius this time of a sector of a circle with a central angle of pi over 4 with an arc length of 3 pi meters. Okay, so let's just draw a picture really quick to visualize what we have. I'm going to draw my best circle here. And we know that we're going to be cutting off an angle of pi force. Well, pi force, that is really 45 degrees. And so let's draw that just as a picture here. If I have a 45 degree angle, if this is my origin, 45 degrees is somewhere like that, if that's 90. So there's my pi force. And we know that the arc length here that's trapped here is 3 pi units from end to end. There we go. And we'd like to find that radius value r. So let's set up our equation to solve that. So we know that the arc length s, again, is equal to theta times the radius r. And so our arc length we know is 3 pi. And that's in meters. So that's telling us what unit of length our radius is going to be in. It's going to be in meters, is equal to my theta, which is in radians, is pi over 4 times my radius, r. So here we can multiply both sides by a reciprocal fraction. We'll call it 4 over pi. And solve for r, the radius. And so pi's will cancel out here, and we'll be left with 12 meters for my radius. So the radius r is going to be 12 meters for this given circle with those components. All right, so those were pretty straightforward in terms of their components. There's not a lot of interpretation for those questions. So let's go into some applications where we might have to interpret some sort of a story problem. So let's look at the first example here, and I'll make sure it's all in view here. We want to consider the pendulum on a grandfather clock swings from side to side once every second. If the length of the pendulum is 4 feet and the angle through which it swings is 20 degrees, how far does the tip of the pendulum travel in 1 second? All right. So if we consider traveling from side to side in 1 second, let's just draw a picture of maybe a pendulum. And this might go back, if you're not familiar with a grandfather clock and how it might look. Let's just consider if we had a clock here, and we'll have a pendulum coming down from this clock, and I'll go from side to side here. Maybe it's on the full left side. We've got a pendulum here, and we know it's going to be swinging from side to side in 1 second. So on its far right reach, we know that this is going to swing through an angle of 20 degrees. So let's continue to label this up a little bit. If we swing through here an angle of 20 degrees, that's right here. And we know the length of this pendulum is 4 feet, so we can label that as well. This is a 4-foot pendulum. we want to know how far the tip of the pendulum travels in 1 second. And remember that from our statement above, the clock swings from side to side once every second. So from side to side goes from 1 second. So in other words, we're going one left to right in 1 second, side to side. So if I consider this is really talking about the arc length that's traveled. How far does the pendulum really travel from side to side? And so what I'm looking for here is really an arc length problem called S. And we know that arc length is going to be trapping an angle of 20 degrees where my pendulum is 4 feet, which is really playing the role of our radius here. This is looking like a sector of a circle here. And so let's consider what we're going to need to do. We know the arc length, again, is going to be my angle theta in radians times my radius. So we need to think about what is this radius going to be in, or the angle, 20 degrees in radians. So let's take 20 degrees here, and we want to convert this. We know pi radians over 180 degrees. And if we look at 20 and 180, we can definitely cancel these out. If we divide by 20, this goes in evenly. That would be 1 divided by 180 divided by 20. Looks like we can get 9. And so when we cancel out those units, we're left with some radian units of pi over 9 radians. So I have my angle in terms of radians, and now I can go over and use this in my arc length formula. So this would be the arc length. That's really what I want to find. The total distance the pendulum goes from side to side is the angle, pi over 9, times the radius of 4 feet. So this would, in fact, be really 4 pi over 9 feet as the arc length, or as the distance traveled over 1 second. If this would have been asking for the distance traveled over, say, 5 seconds, we just have to multiply this arc length back and forth 5 times. So this happened to be just 1 second, and we were traveling back and forth every second. So this is simply going to be finding that arc length. Okay, let's take a look at a follow-up example for this. This is asking, in the next example, find the total distance traveled in 1 minute by the tip of the pendulum on the grandfather clock. So if we found how far it travels in 1 second, now we can just consider, what if we wanted it to travel in 1 minute? How far is it going to be traveling? Well, we know the arc length for just a second. Now we can just multiply this by a conversion of 1 to 60 to find how many times it's going, or how far it's going to go in 1 minute. So if it goes 4 pi over 9 feet, and we can consider this as a time interval now, or a speed, in 1 second. It's really a speed here, or a rate. I want to know how far it's going to travel in 1 minute. Well, that would say that every 60 seconds per minute. And so if I multiply by 60 here, I could get the following. This is going to be 240 pi over 9 feet. And this is going to be feet per minute now as my rate, feet per minute. If you'd like, we can reduce this down just a little bit. Reduce by 3, and this gives us 80 pi over 3. And we'll go feet per minute. Would be our rate. And so we are actually going 80 pi over 3 feet in a full minute. for this grandfather clock. All right, in our next video, we will be taking a look at the idea of sector area. So I hope you guys stick around for that next video. Thanks.